Hello, class, and welcome back. So today I'm going to start with chapter 3. And this course, remember, is statics. It's about statics of rigid bodies, statics of particles. Okay. Where we're looking at objects in equilibrium or at rest or moving with constant velocity. So in chapter 2, what we're doing was just looking at forces. Okay. It's not only forces that actually act on our rigid body or particle. There could be movement and other stuff as well. So we look at forces. And now we are looking at equilibrium of a particle because a particle can only move in a straight line. But rigid body can move in a straight line and then also kind of rotate. So you're going to realize that the next equilibrium we're going to look at is going to look at equilibrium of a rigid body. But that is not chapter 4. That is chapter 5. Because there's another loading, not just forces, but forces. When it's a rigid body, we can have movement. So chapter 4, we're going to talk about movement and other stuff before we do equilibrium of rigid body in chapter 5. So this chapter 3 is about equilibrium of a particle. And we said the particle is, we just model it, an object, because we are taking the mass or the weight into account, but we are neglecting the size or the dimension. If you look at the picture here, this is like a crane lifting some kind of load. And we have to decide, or we have to design the crane so that it doesn't fail. We have to design the crane, the hook that is holding the load so that it doesn't fail. Okay. In order to do all these things, we need the force. So, and also you have to select this cable or rope so that it doesn't kind of break. So we need the tension, we need the force. We need to find the force or tension in this cable in order to be able to design this and design the hook, etc. And then to raise some kind of maximum load that we're looking for. So we can model this weight as a particle. So you can model it as a particle. Okay, so it will have its weight, and then that. So this is a particle, like a point mass. Another way to put it, we say a point mass. A point mass. Okay? And the T will be the tension. Anytime we cut a rope, we have an arrow here, and arrow going the opposite. Newton's third law. Okay? So we'll look at equilibrium of a particle in 2D and then 3D. And to do that, we need to include the concept of free body diagram. Okay, free body diagram. So we'll do 2D, that's coplanar, and then we'll also look at it in 3D, and that's what we're going to do that. Okay. So what is a particle is said to be in equilibrium, but when it's equilibrium, we also have what we call dynamic equilibrium. We'll do that in dynamics class. So equilibrium, normally when people say equilibrium, they normally meant the static equilibrium. So it's when the object is in equilibrium means it's at rest, or it's moving, it's in motion, but it has a constant velocity. Okay. So if you remember, I said the equilibrium of particle have to do with the Newton's first law. Equilibrium of particle have to do with Newton's first law. And what is it? What's the main condition? We are neglecting the size. So it can only translate in a particular line or axis. So the sum of forces should be balanced. Or we say the sum of forces in any direction should be called the sum of forces in the opposite direction. In vectorially in general, we say the vector, sum of the vector is equal to vector O. when we write it, we can write like this, equal to vector O. Okay, or the resultant force, as we should say, equal to O. Okay, in 2D, then this is like OI plus OJ In 3D, then there's like OI plus OJ plus OK. So vectorially. We can break this one into scalar, and that's what normally you guys used to say. We can break this one to scalar because the resultant alone can be written as a vector, can be written as FR in the XI. Let's say FR in the YJ, FR in the ZK. And if the particle is in equilibrium, then these components all have to be zero. These components all have to be zero. Or we can use the concept of sum of forces in any direction is zero. So normally we'll deal with the X, Y, and then Z. So summation of forces in the X is zero, summation of forces in the Y is zero, summation of forces in the Z is zero. Okay. And that's what we meant by a particle is in equilibrium. So if the particle is equilibrium, this is the condition for equilibrium. Condition for a particle to be in equilibrium. Condition for a particle to be in equilibrium. Okay. Of course, when we say we're doing static, means acceleration is zero. Acceleration is zero. Okay. So we talk about free body diagram. Normally in short, I say FBD. Free body diagram, FBD. So what is a free body diagram? If you ask people a couple of free body, I wish we are in class, then I'll ask what is a free body diagram. But I don't say forces, that. It's have to do with the object, the body. Okay. So we like to draw an object of interest or the body of interest, and then we show all the known forces on it. Sometimes there's also unknown forces. We show all of them. Sometimes the unknown forces, we don't know which direction they point into. So you put them somewhere. And if you calculate them, they are positive, then it means they are exactly where you pointed them to. If they are negative, means it's opposite to what you show on your free body diagram. On the free body diagram too, we show distances, angles, measurement, etc. Okay, and that's what we meant by free body diagram. Sometimes you can have more than one object. So you have one object connected to another object. This is object A, object B. We can separate them, object A and then object B or object D. And then we draw the FBD of this. We draw the FB of this. Normally, if they are in contact, then wherever they are in contact, you can have like Newton third law, okay? Some kind of reaction. Okay, and so on and so forth. So we have to be drawing free body diagram in this chapter. You can't just calculate, you have to draw free body diagram. So I will go through some few things that we need when you are drawing free body, which comes in our system. And after that, we'll draw some few free body diagram. So let's start with a spring. A spring. Yes, we have something called which we see as spring, but later on, it's not every time we have a spring. We can also have a bar. You see, I can have a bar like this. The bar can also have some kind of spring. So we can also represent the bar as kind of a spring. So it's not all the time that when you say a spring or a structure has a spring, a stiffness, yes, stiffness. Okay, then that. So, but few assumptions in this class, if you are doing for a spring, we're going to say it's light, means we are neglecting its weight or mass. Simple, because we can have a very complex spring. Linear, elastic. That is, if you take any spring and you keep on adding some weight or mass, and you measure the force against the extension X, or you can say X, then we are assuming they're going to be a straight line. And if you remember, the spring force F equal to K times extension. The K is called the stiffness of the spring, or the spring constant, or the spring rate. You have a couple of them. Okay. So the slope of plotting that, the slope will be K. If you plot the extension against this, it's also going to straight line, but the slope will be 1 over K. So just take note. Let's take note. So let me clear the screen here. So if you have a spring, it might have an original length, let's say L0, and then you pull it. or you attach some kind of weight. So let's say the new length is L. So the extension X, as is shown here, is your new length minus the original length. That's how we measure extension. That's how we measure extension. And I believe most of you have seen this formula before, F equal to KS. The spring force is proportional. The spring force is proportional to the extension. If you remove the proportional sign, then the spring equal to a constant X. This constant is what we call the spring constant or the spring stiffness. The spring constant or the spring stiffness. The next I want to talk about is pulleys and cables and stuff. If you have a rope going around a pulley, so we have a pulley here. A pulley is normally attached and you have a rope going across it. So the pulley is kind of fixed at the middle. Yeah. The pulley have a groove where you have a cable that can go across. If we say the pulley is frictionless or there's no friction, then it means the tension on this side, if the tension on this side is T1 and the tension on this side is T2, that if the pulley is frictionless, then T1 is equal to T2. Or in other words, we say the ropes or the cable is freely to move. It's free to move, then T1. But if we are taking friction into account, then T1 is not equal to T2. In fact, there's a formula that, if time permits and we do friction, we're going to talk about. There's a formula that connects this one to the coefficient of friction. We'll talk about that. Another thing I want to talk about next is, and sometime let me clear the screen. So instead of saying T1, T2, we just call it the tension T. It doesn't matter whether the pulley, let me draw a pulley, the ropes are like this, or the ropes is at an angle theta. It doesn't matter. So far as it's frictionless, that. So these are a few things that we coming up to make our model. Okay. Another one is cables. You suspend an object on a cable. So let's say you have a roof or something, and you have a ceiling fan. You have a ceiling fan. So that I can draw a ceiling fan. Ceiling fan. Is it four blades or 3 blades? Okay, whatever. Okay, so you have some science with ceiling fan. So this will have a weight. Normally weight, we can say the mass is M, the weight is mg, or we can just say W for weight, where W is equal to mg. So we can cut, you can cut the cable, you can cut like that. So let's take this mass, you cut this. We can draw the free body diagram of the mass here. So if you cut, anytime you cut, let me clear the whole screen. Anytime you cut, and I'll draw the free body diagram of this. You show an arrow here. Newton tell you have an arrow here, and they are balanced. So you show an arrow here. We can call this a T for the tension, or F or something, or P in it. Then there's a weight, which is coming down. So you can call the weight mg, or sometimes people can just call it W, where W is the weight. Strictly speaking, that object or mass has a center of gravity somewhere. Okay, center of gravity C. So this is actually going from the center of gravity, but if you just show it here, no problem. Okay. Now, if you do the free body diagram of the object, okay, that is the mass M. We can also draw free body diagram of this side, which is the cable, the roof. So that is the roof here. So the roof here, and then I can show this T, because it have to be opposite. This have to be opposite to balance. And what is balancing this one? There could be a reaction here. There could be a reaction, which I can show the opposite. Let's say N. Okay, let's say N. Oh, later on, we're going to apply condition of equilibrium that the forces should be balanced. So if you take, for example, this one, we're going to say what T is equal to mg, or from here T is equal to W, and here T is equal to N. In other words, if you keep on drawing this free body diagram to that, that means whatever the weight is whatever is pulling the roof. Is pulling the roof. let me do, so that's few things I have here. Either the mass, the weight, mg, all that. Okay. I like to make the videos very, very short. So let me end the video here, then I'll do a second one so that I can wait to post in your WhatsApp. Okay. So that's the first video for that. When we come back, I'll do 3 examples on how to draw freeboard diagram. Okay. Bye-bye.